All right. So before I just jump in and I guess go through questions in chapters 4 and 5, did you have any specific questions that you wanted to go over from those chapters?
So I don't really understand. I was trying to do the ones on the online,
Sure.
and they ask a lot about like page 148,
Okay.
the units of radiation measurement.
Okay.
And I don't really feel like the questions. Okay, maybe 5.27.
Okay.
Or 5.28.
Okay.
I'm not quite sure what to do with those units of radiation measurement. I don't get the conversions and
Okay. All right. So let's take a look at that. So we'll start with 5. Let me get my pen. Oh, sorry. Just got to do one quick thing. I forgot to link. All right, so let's start with 5.27. Sorry, just give me 1 second.
actually, could we start with 5.25?
Sure. Just gotta. Okay. Yeah, my iPad wasn't picking up my Apple Pencil. But I think that was it. All right, 5.25. 2 technicians in a nuclear laboratory were accidentally exposed to radiation. If one was exposed to 8 milligrays and the other to 5 rads, which technician received more radiation? All right, so 5.25. So we've got one technician, looks like got 8 milligrays of radiation. And one technician had 5 rads of radiation. And they want to know which technician received more. More radiation. All right, so essentially we got to convert these to a common unit to figure out which absorbed more radiation. So when we talk about the radiation absorbed dose, so RAD, all right, that is the unit that measures the amount of radiation absorbed by a gram of material such as body tissue, where the radiation equivalent in humans, REM, is a unit that measures the biological effects of different kinds of radiation. So essentially, I think what we're looking for here is which one of these has the higher radiation absorbed dose. So because this is the unit that measures the amount of radiation absorbed by a gram of material. All right, so 1 gray, 1 GAY, is equal to 100 rad. So the question is, if we have 8 milligrays, how many rads would that be? So the first thing we'd want to do is we'd want to take the 8 milligrays and multiply that by 1 gray over 1,000 milligrays. Because just like we talked about with liters and milliliters, what's the equality that we would use here? That
Right.
essentially 1,000 milligrays is equal to 1 gray.
1 gray. Okay.
So if we plug that into our calculator, that gives us 0.008 grays. Okay. So now we want to convert that into rads. So we multiply that by 100 rads over 1 gray. So then we move the decimal point back 2 places to the right, and that gives us 0.8 rads. So what that tells me,
Okay.
this technician absorbed the most because he absorbed an equivalent of a radiation absorbed dose of 5, whereas the person who had 8 milligrams of radiation absorbed a radiation dose of 0.8. Okay. If we went the other way around and converted the 5 rads into milligrams, we would find that the 5 rads would be more than 8 milligrams. So
Okay. So
either
you
way,
can go either way.
yeah, I think so, because basically they're both sort of units that in terms of rad, like, it's to me sort of like an arbitrary unit in a sense. Gray is more of a unit that I sort of think of as like the liter or the the liter or the gram or something along those lines.
Okay.
So, but I think you can go either way, and you would definitely have that the second technician, absorbed more. Because if we did it the other way, then we would take the 5, and so we would take the 5 rads and divide that by 100. Just gonna pull out my calculator, do that quick. So we would take the 5 divided by 100, but then we would multiply that by 1,000.
1,000 because it's M.
Yep, and that would give us 50 milligrams. So 5 rad would be the same as 50 milligrams. So either way, the
Which is
second,
less than 8.
yeah. So either way, the second technician absorbed more radiation.
Yeah, just the terminology, I just don't quite understand. Like, what am I supposed to do with this rad and gray? I don't
Yeah.
understand.
So basically, the rad and the gray, they
Okay.
are linked together to sort of measure the absorbed dose.
Okay.
And again, that could be almost sort of anything. The most common, thing would be to measure it in terms of body tissue, but it could even be something, like I'm trying to think of something off the top of my head. It could be anything in reality that could sort of absorb different types of radiation.
Okay.
But they're sort of linked to each other by a measurement of the absorbed dose, where the REM, the radiation equivalent in humans, and this Sievert, this SV, they sort of measure the biological damage.
Okay. So they would have to give me the SV if I were to do it in REM.
Yes.
Is that right?
Or there is, I believe, so essentially, if you wanted to convert between rads and REM, the equation is that REM is equal to the rads times what they call the factor, which I sort of like to
Yeah.
describe as the biological factor for
Okay, I see that now on page 148 and where you're getting this.
the type of radiation.
Okay.
And it's, I think for 2 of them, it's the same. Yeah, here it is. So for beta and gamma radiation, the factor is 1. So for beta and gamma, the factor is 1. So basically for beta and gamma radiation, the radiation absorbed dose is equal to the radiation equivalent in humans. But for alpha particles, the factor is 20. So, I mean, how much memorization are we going to do? If we had a question like this, I would probably give you the proper equality
Okay.
and essentially the factor as well. And
Okay.
you would have to remember, how to sort of solve it. But again, I don't expect every equality to sort of be memorized. So, I would guide you along with that to the best of my ability, and also with the factor as well. And then you would have to sort of solve based
Okay.
on, what they're asking for.
So yeah, if we could do 5.27,
Sure.
because that has to do with the Curie one.
Okay, so 5.27. So the recommended dosage of iodine 131 is 4.20 microcuries per kilogram of body mass. How many microcuries of iodine 131 are needed for a 70.0 gram person with hyperthyroidism? Okay, so this 4.20 microcurie per gram is essentially, or per kilogram, sorry, is essentially a conversion factor.
Oh, okay.
So if we have a 70 kilogram person, we're basically going to multiply that by 4.20 microcuries per kilogram. Because when we do, what happens to the kilogram is going to cancel.
Okay.
So if we take 70 and multiply it by 4.2, that would give me 294 microcuries. Okay. And that would be my answer there.
Sure. Okay.
And then for B, it says a person receives 50 rads of gamma radiation. What is the amount in grays? So
Great.
we have 50 rads. And going back to the proper
Okay.
equality, we have
100 rads.
Yep.
1 gray equals 100 rads. Okay.
Yep, that's right. So we're going to take the 50 rads and we're going to multiply it by 1 gray over 100 rads.
Okay.
The rads cancel, and 50 divided by 100 is 0.5 grays. So that would be our answer there. Other questions?
Nope, I think that's it.
Okay.
I just didn't know how to apply. I understood that the information was coming from that chart, but I didn't quite understand how to.
Yeah,
apply
it's a little bit unclear in general, the relationship between rads and REM and such like that. But basically, the rads would be the radiation would be a measurement of the absorbed dose. And then the REM would be, okay, what would be the biological damage done in a sense? And they call that the radiation equivalent in humans. Because a lot of the times the way they figure out what the biological damage would be is that they don't sort of put the types of radiations onto humans directly. They'll do some other types of material, but then they'll have to equate that to what the biological damage would be if they're human, or were to absorb that dose of radiation. So
Okay.
basically we start by sort of ascertaining the radiation absorbed dose, and then we sort of equate that to the radiation equivalent in humans and such like that. And I forget and then I think there's like a number, which you don't have to memorize, that sort of corresponds to a lethal dose. I think it's like 500 REM or something along those lines. I forget the exact number. I haven't looked at it. in a while, but I think it's like if it's 500 REMs or greater, I think that's when it's a lethal dose and such.
Okay.
Looking to see if they have it here quick, and then I'll start to go through. And actually, they changed it. They changed it to, I guess, in the older text they had it in, but now they changed it to sieverts. So
Okay. Yeah.
yeah, so for humans, 5 sieverts is the lethal dose,
Okay.
which corresponds to 500 REM. Okay. All right. Let's go back to, I don't know if anybody else is here. Let me just check. I don't think so. No. All right. So let's go back to chapter 4. And I want to do a little bit of practice in that. First, looking at some questions dealing with the periodic table. You know, the periodic table is really the most important reference table that we have in chemistry. And it's really something that students have to get used to using. They have to be familiar with the terminology that's involved, groups and periods, identifying mass number, atomic number, things of that nature, and such like that. So just go back and give sort of a.
Can we use this one in our book as the one we use for the test or not?
Basically, what I put in the announcement was that you can use whichever periodic table that you like, as long as it's basically blank in terms of, you know, like, for example, in this periodic table, if I wanted to use this, I could, but it can't have any of your own writing on it.
Okay.
It's my only requirement.
Yeah.
But I don't think it's sort of fair to make students use a periodic table that they haven't seen before. So
Right.
I'm okay with allowing students to use whatever periodic table they're most comfortable with.
Okay.
All right, so quick sort of run through. Your horizontal rows are your periods, numbered 1 through 7. Your vertical columns are your groups, numbered 1 through 18. Now, the groups can also be numbered with A's and B's. Okay, so essentially on the ends, you have, or I shouldn't say on the ends, but on the upper parts of the periodic table, you know, you have all your A's, 3A, 4A, 5A, 6A, 7A, 8A. Okay, these are your main group elements. And then in the middle of the periodic table here, you essentially have all your B groups that are present. Remember, your A's are your main group elements, and your B's are your transition
Okay.
elements. And as we go through the course a little bit later on, you know, you'll start to see some real differences between them. So one way that the periodic table is divided is into groups and into periods. The other way that the periodic table is divided is into metals, nonmetals, and metalloids. You know, a lot of times with the periodic table, a lot of periodic tables have a bold zigzag line that starts at the top of boron and then works its way down and to the right. And essentially what we find is that the elements located along that zigzag line are essentially your metalloids. The one exception is aluminum. Aluminum is not a metalloid. Aluminum is a metal. So basically boron, metalloid, aluminum, metal, and then silicon, metalloid, germanium, metalloid, arsenic, metalloid, Sb, Te, and then finishing up with Po, your metalloid. Then all of the other elements to the left of that line are your metals, and then the elements to the right of that line are your nonmetals. Right. Now, just to also mention, at the bottom here, you have these two subperiods, what are known as the lanthanides and the actinides. And as you see here, they actually, the lanthanides belong as part of period 6, and the actinides belong as part of period 7. And the reason why they're not actually included in there themselves is because if they were, the bottom 2 periods would be a lot longer than the rest of the ones that are above it. And that would sort of throw off the symmetry that's involved in the periodic table. All right, so that's why they're at the bottom. All right. The atomic number for each element, what does it represent? Essentially, the atomic number represents the number of protons that an atom of an element has. And remember, the way that elements are distinguished from each other is that no 2 elements have the same number of protons in the atoms that they possess. Okay, so that's why essentially here every element has a different atomic number, because there are no 2 elements whose atoms have the same atomic number. The average atomic mass. So a lot of times we refer to the average atomic mass as also the mass number. Okay. So a lot of times the average atomic mass is also referred to as the mass number. Now, at this point, we learned about that the mass number essentially is equal to the number of protons and the number of neutrons that an atom has. And when we're figuring out the number of neutrons, essentially we take the mass number and we round it to the nearest whole number. And to get the number of neutrons, essentially in the highest or the highest percentage isotope of an element, we subtract the mass number from the atomic number. And that essentially gives us the number of neutrons in a sense of, if you have different isotopes of an element, and most elements do have different isotopes, you would find the number of neutrons in the isotope that occurs the most. All right. Electrons. Remember, all atoms are neutral. So the atomic number for an atom not only tells us the number of protons, but it also tells us the number of neutrons. Okay, so keep that in mind. So protons, neutrons, and electrons. All right. So some names that are involved with the groups that you should be familiar with. So remember, group 1A are your alkali metals. Group 2A are your alkaline earth metals. Group 7A are your Group 7A are your halogens, and Group 8A are your noble gases. So keep that in mind as well. You know, those names are used sort of quite often. So you do want to be familiar with those names. All right. So let's take a look at a couple of questions from the textbook. The first one I'll take a look at is 4.8. And 4.8 says, identify the group or period number described by each of the following. All right. A says, contains sodium, potassium, and rubidium. So sodium, potassium, rubidium. Are they in a group or are they in a period? They are in the same group. Why? Because they're in the same vertical column. And what group number would that be? That would be 1 or 1A. Letter B begins with beryllium. Okay, so beryllium is not at the beginning of a period. Beryllium is at the beginning of a group. And because essentially when you look at periods are essentially read from left to right, and groups are essentially read from top to bottom. So what group is beryllium a part of? Beryllium is a part of group 2A or 2. That's the group that begins with beryllium. Contains the noble gases, all right? Noble gases, the elements in group 18 or 8A. Okay? And then contains boron, nitrogen, and fluorine. Boron, nitrogen, and fluorine are all in the same horizontal row. So they're all in the same period. What period is that? That is period 2. Okay. All right, let's take a look at some parts of 4.10. Give the symbol of the element described by each of the following. Letter A, the alkaline earth metal in period 2. So period 2 Where do we find the alkaline earth metals? We find the alkaline earth metals in group 2 or 2A. So basically you sort of like, it's like coordinates on a graph, you sort of want to find where they meet. So period 2, group 2A, beryllium, okay? That is the alkaline earth metal in period 2. Letter B, group 5A, period 3. So group 5A, period 3, that brings us to phosphorus. The noble gas in period 4. So we're looking at the noble gases. The elements of group 18 are 8A, period 4. So period 1, period 2, period 3, period 4. Okay, here's period 4, all the way across to here. Krypton, okay, would be the element that we're looking at. The halogen in period 5. So the halogens are the elements of group 17 or 7A. Period 2, period 3, period 4, period 5. We're looking at iodine, okay, as our answer. And then finally, group 4A, period 4. So here's group 4A, period 2, period 3, period 4. We're talking about germanium as our answer. All right, let's jump to, let's go to 430. Okay. 430 asks, how many protons and electrons are there in a neutral atom of each of the following? Okay, so how many protons and electrons are in each of the following? Letter A is carbon. Okay, so carbon has, and I'm also going to do neutrons as well. All right, so we'll do neutrons with these also. So this is 430, and we'll do neutrons with this as well. So carbon has an atomic number of 6. Okay, that's right here. Okay, carbon has an atomic number of 6. So what does that tell us? It tells us that now we not only do we have 6 protons, but we also have 6 electrons. Now, what about the number of neutrons? We'll take the mass number for carbon, which is 12.01. We'll round that to 12. Okay, 12 minus 6, 6. So typical carbon atom has 6 protons, 6 neutrons, 6 electrons. Okay, so that's the first one. B, fluorine. All right, so here's fluorine right here, chemical symbol of F. It has an atomic number of 9. So it has 9 protons, 9 electrons. Remember, all atoms are neutral. How many neutrons does a typical fluorine atom have? Well, it has a mass number of 19, which we don't have to round, is exactly 19. We'll subtract from there 9. 19 minus 9 is 10. Remember, the protons and the protons and electrons always have to be the same. The protons, electrons, and neutrons can be the same, but all 3 of those numbers don't have to be the same. And in fact, we'll talk about isotopes in a moment, where you could have atoms of the same element that actually have different numbers of neutrons. Okay? So that's fluorine. Tin. All right, tin. Chemical symbol of SN. Okay, so atomic number of 50. Okay, so what does that mean? It means it has 50 protons, 50 electrons. Okay, the mass number of tin is given here as 118.7. So we would round that up to 119. 119 minus 50 is 69. Okay, so that tells us essentially that for tin, the most common atom of tin that we come across, the number of neutrons present is going to be 69. Okay, and then finally nickel. So nickel, atomic number of 28. So that tells us that we have 28 protons, 28 electrons, because again, all atoms are neutral. But how about the number of neutrons? So we'll take 58.69, that's given here. We'll round that up to 59, okay? We'll subtract 59 from 28. 59 minus 28 is 31. So essentially for nickel, we would expect to find for nickel atoms 31 neutrons that are present. Right? What I've seen a little bit is I think some periodic tables have slightly different, for some reason, slightly different average atomic masses and such like that. So, if a question on the exam, I'll double check to make sure, whether it's an element where the atomic masses slightly vary based on periodic table, especially, and such like that. But, if it's off, I don't think there'll be two answers where, you'd have 28 neutrons and 29 neutrons. So, the answer would be pretty obvious. So if there's a little bit of a rounding error, we should be fine. But yeah, I think there's one or two periodic tables I've seen where the numbers are slightly different, but they should be uniform. But for some reason, sometimes there's slight variations. So, but I wouldn't go crazy worrying about that. All right. So let's talk a little bit about isotopes. Okay. So essentially, isotopes are atoms of the same element that have different numbers of neutrons. If I were to go to the lab and get a box of carbon atoms, I could pick 1, I could pick 10, I could pick 100, I can pick 1,000,000, I could pick 3 trillion. Every single carbon atom is going to have 6 protons. And the reason why is because, remember, every element is defined by the number of protons they have in their atoms, because no two elements have atoms that have the same number of protons. However, not all of those atoms of carbon are completely identical, because most of the carbon atoms I would pick out of that box would have 6 neutrons. But the trick is, not all of them would have 6 neutrons. Some of them would have 7 neutrons, and then others would have 8 neutrons. Now, how do I know that? I just know that because I've dealt with carbon for many years. In fact, the periodic table doesn't necessarily tell you that information, because based on what we did in the previous example, we would think for carbon that essentially every single carbon atom has 6 neutrons. The reason why in the periodic table, the mass number or the average atomic masses are not whole numbers is because essentially they're a weighted average of the percentages of the different isotopes that are present of that element. So it's sort of a weighted average based on the percentages and essentially the masses, usually given in atomic mass units, of the different isotopes of that element that are present. Most of the carbon atoms you come across have essentially 6 neutrons associated with them, but not all of them. So that's why the mass number is not exactly 12, it's 12.01, because there are some that have 7 neutrons or a mass number of 13, and some that have 8 neutrons or a mass number of 14. So one of the things I always tell students is with the periodic table, for protons and electrons, you can use the periodic table without hesitation. But for the number of neutrons, make sure you read the question carefully. Where they're giving you information about the mass number, talking about an isotope and such like that. Now, if they give you no additional information, like in the example we did where we said, find the number of protons, neutrons, and electrons in carbon, then you have no choice but to use the periodic table. But as you'll see in some of the examples we're about to do, there'll be some additional information that when we sort of find the number of neutrons, we might have to question a little bit about the periodic table. And I said, and I wouldn't necessarily rely on the periodic table to find the number of neutrons. Okay. So let's take a look at a couple of examples. That fall into that category. Okay. So let's take a look at 4.36. Okay. So it says, write the atomic symbol for the isotope with each of the following characteristics. So just to sort of, for an atomic symbol, You have the chemical symbol in the middle. You have the atomic number in the lower left. And you have the mass number in the upper left. All right. So those are a little bit about atomic symbols. So 436, letter A. We have an oxygen atom with 10 neutrons. Okay. So chemical symbol for oxygen is O. That doesn't change. If we go to the periodic table, oxygen has an atomic number of 8. Okay. Now, because we're dealing with an oxygen atom that has 10 neutrons, how do we figure out the mass number? Well, we're going to add 10 plus 8. So that's going to give us a mass number of 18. And if you notice the periodic table, and this one is accurate, dead on with this, oxygen has a mass number of 16, but not for this isotope. For this isotope, it would have a mass number of 18. So that's why I said, when you look at the question, make sure you look at the additional information that's given. Letter B. 4 protons and 5 neutrons. Now, one of the things you could be saying to yourself is, well, wait a minute, how do I know what that element is? Well, again, elements are identified based on the number of protons. So if we go to the periodic table, the only element that has 4 protons, the only element with an atomic number of 4 is beryllium. So we know the chemical symbol here is going to be Be. The atomic number is going to be 4. And since we have 4 protons and 5 neutrons, the mass number is going to be 9. Okay. Let's look at letter C. 25 electrons and 28 neutrons. Now again, what element are we dealing with here? And if you think about it, we actually are given the number of protons. How is that the case? Remember, isotopes are atoms, okay? And all atoms are neutral. So since we have 25 electrons, it also tells us that our substance here has 25 protons. So if we go to the periodic table, the only element that has 25 protons, the only element with an atomic number of 25 is manganese. Okay. So chemical symbol of Mn, atomic number of 25, 25 plus 28, 53. So the mass number of the manganese here would be 53. Okay. Let's do one more. Letter D. Okay. So we have a mass number, right? A mass number of 24 and 13 neutrons. All right. A mass number of 24 and 13 neutrons. So how do we know what element it is? So remember, the mass number is equal to the number of protons plus the number of neutrons. So we're given the mass number, we're given the number of neutrons. What does that allow us to find? it allows us to find the number of protons. So we'll take 24 minus 13, and that tells us that we have 11 protons. And if we go back to our periodic table, the only element that has 11 protons, the only element with an atomic number of 11 is sodium. Okay. So chemical symbol of N, Na, not N, sorry, N is nitrogen, sodium is Na, 11 protons, which would be our atomic number here, and the mass number would be 24. All right. So always like talking about isotopes a little bit because of the ideas of the neutrons and having to figure, that part of it out. All right. All right. What I wanted to do a little bit was to actually jump a little bit into chapter 5. And what I wanted to spend a little bit time talking about is half-life. So half-life is the time it takes for a radioisotope to decay to 1/2 of its amount. Some radioisotopes, remember, what are radioisotopes? Those are isotopes that release different forms of radiation to go essentially from higher in energy to lower in energy. And remember, the 3 common types of radiation that you come across are your protons, your alpha particles, your beta particles, and your gamma rays. Okay. So remember, your alpha particles essentially contain 2 protons and 2 neutrons, and therefore are given by the atomic symbol 4,2 alpha or 4,2 He. Why helium? Because the only element in the periodic table with 2 protons is helium. But remember, an alpha particle is not identical to a helium atom, because a helium atom not only has 2 protons, it also has 2 electrons. An alpha particle has 2 protons, but it has no electrons. An alpha particle has a +2 charge, where a helium atom, just like all atoms, is neutral. Your beta particles are essentially electrons that are released from a radioisotope when essentially protons change into, let me just double check because I'm pretty sure, when protons change into neutrons. Or actually the other way around, my apologies. It's when a neutron changes into a proton and an electron. So 10N goes to 11H plus 0 minus 1E. Yep, that would be a balanced nuclear equation. So essentially there, when your neutrons change into protons, and along with that, you get a release of an electron. Speaking of the atomic symbol for an electron, the atomic symbol for an electron is 0 minus 1E. Okay, and essentially that would be the atomic symbol for a beta particle. Sometimes you see it as 0 minus 1 beta. Right. And then finally you come across your gamma rays. Now essentially gamma rays are considered to be pure energy. The biggest difference is that when alpha particles and beta particles are released, you actually have a change in the number of protons that are present, and a change in the number of neutrons as well. The change in the number of protons actually changes the identity of the element. gamma rays, when a gamma ray is released, there's actually no change in the number of protons or neutrons. The way I like to describe it, in the sense, is that you have a nucleus that's very messy, and that very messy nucleus is made to be more organized. Goes from a less stable state to a more stable state, and that also results in a release of energy in the form of a gamma ray. So your gamma rays are essentially pure energy. The biggest thing to remember, as I mentioned, is that there's no change in the number of protons or neutrons. So essentially the identity of the element is going to be the same. The difference is going to be, it's going to be going from a higher energy to a lower energy, and therefore it's going to be more stable. All right. So those are your three main forms of radiation. I also want to mention, since it's on my mind, the atomic symbols for a proton, which could be written as 11H or 11P. Again, why would we use hydrogen? Because since you have one proton, the only element in the periodic table with one proton is hydrogen. But again, keep in mind, a hydrogen atom is not the same as a proton, because a hydrogen atom not only would have one proton, it would also have one electron. A proton has one proton, it has 0 electrons. A proton has a +1 charge. We'll see that essentially a proton is equivalent to what is known as the hydrogen ion. We'll see that in short order. Okay. And then for your electrons, which we did, 0 minus 1e. And then for your neutrons, you have 10n. 11H, one proton, no neutrons, 1 plus 0 is 1. For neutrons, 0 as the atomic number, because there's no protons, but there's one neutron, so 0 plus 1 is 1. Small n, small e, small p. Okay, keep that in mind as well. Small letters for those. All right. So let's take a look at a half-life example. All right. So let's take a look at let's take a look at 5.32. So we have a sample of sodium-24 with an activity of 12 microcuries is used to study the rate of blood flow in the circulatory system. If the half-life, if sodium-24 has a half-life of 15 hours, okay, what is the activity after? And they give you a couple different scenarios. We're not going to do all of them, but we'll do a couple of them. So first off, let's do B, which would be 30 hours. Okay. The way that I like to solve half-life problems is I sort of just like to set up a chart, keeping track, or actually starting with the amount or the activity in this case, which is fine. Usually you're dealing with like 1/2 the amount. In this case, you're dealing with the activity. Fair. It's not going to really change what we're going to do. What I like to do is start with that initial amount, and then I keep track of each half-life and the total amount of time that has passed. Okay. So in this example here, I would start with my 12 millicuries. And this is essentially where time would be equal to 0. Okay. So what happens? I now have my first half-life. And when I do this, each half-life, in a sense, I like to use an arrow to indicate each half-life. So the half-life is 15 hours. And therefore, starting at time equals 0, how much time has passed total? Well, 15 hours has passed total. What would be the activity? At each half-life, the amount, usually grams, but in this case, the activity would be cut in half. So 12 divided by 2 would give us 6. Now, do we have our answer? No, because we don't want 30 hours. We don't want 15 hours total. We want 30 hours total. Right? So let's continue. So for our next half-life, which is again 15 hours, 15 plus 15 would now give us 30 hours total. So guess what? After this point, we have, excuse me, we would have reached where we should have been. So now I do 6 divided by 2. 6 divided by 2 gives me 3 millicuries. So the activity after 30 hours would be 3 millicuries. All right. Let's do one more of this. Letter D. 2.5 days. So I'm going to do a little bit of extra work first. There are 24 hours in a day. So I'm going to multiply that by 2.5 days. And when I do 24 times 2.5, and then, no, I shouldn't need a calculator to do this, but okay. 24 times 2.5 is 60 hours. Right? And I really want to do that because the half-life is in hours. So I want to know what's the total number of hours in 2.5 days. So we've sort of done some of this already. 12 millicuries. Okay, that's the activity at time equals 0. Our first half-life, which is 15 hours, which would give us 15 days total. Would take us down to 6 millicuries. The next one, 15 hours, which would take us to 30 days total, 30 hours total. $30 hours total. Did I do that on the other one? No, good. All right, and then here, not 30 days total, times it. So 30 hours total. That would take us to 3 millicuries. So we're not at the 60 hours yet. Let's do another 15 days, which would now, God, I am stuck on days. Sorry. Let's do another 15 hours. Maybe it's been a long day. Let's do another 15 hours, which would take us to 45 hours total. So that would take us 3 divided by 2 is 1.5 millicurie. We're not there yet. Let's do another 15 hours, which now would take us to 60 hours total. So now we're at the prerequisite time. 1.5 divided by 2 should be 0.75. I just want to check. Yeah, would be 0.75 millicurie. The biggest mistake I see students make with these examples is that they don't realize the amount that they're given is time equals 0. You know, this is not after the first half-life. This is before we're even starting to count what the half-life is. So, you know, you just want to be cognizant of that because that's the biggest mistake I see sort of students make with these types of examples. All right. All right. So to finish up for tonight, let's do a couple of balancing nuclear equations. So remember, for balancing nuclear equations, you want the atomic numbers of the elements or the particles on the reactants and product side to add up to be the same. You want the mass numbers of the elements, the particles on the reactants and product side to add up to be the same. Now, those two sets of numbers don't, you know, the atomic numbers and the mass numbers don't have to add up to be the same, but essentially the atomic numbers on both the reactants and product side should add up to be the same. The mass numbers on the reactants and the product side, they should add up to be the same as well. All right. So let's take a look at some examples. Let's look at 5.20. All right. So here's our first one. we've got 11,6 carbon going to 11,5 boron plus question mark. So what's our question mark here? First thing I want to do is I want to figure out the atomic number of our mystery substance. So on the reactant side, we have 6 for our atomic number. 5 plus what gives me 6? 5 plus 1 gives me 6. So our mystery substance here has an atomic number of 1. So mass number. On the reactant side, we have 11. On the product side, 11 plus what gives me 11? It's not a trick question. 0. Okay, gives me 11. Now, what's the symbol for this? So one of the other particles that I forgot to mention, and I'll do it now and I apologize, is the positron. The positron is very similar to the electron, but for the positron, you don't have a -1 charge. Essentially, you have a +1 charge. So a lot of times a positron given by the atomic symbol 0 plus 1e. It's not the same as a proton, because for a proton, the mass number would be 1. So that's one of the ways we sort of distinguish between that, because here, yes, both the atomic numbers here are 1, but essentially the positron is more similar to the electron, except their charges are different. So here we would have E. Okay. And essentially what we're looking at in this case as the mystery substance is the positron. Okay. So this was A. Let's take a look at B. All right. So we have for B 3516S going to question mark plus 0 minus 1e. All right, so first off, atomic number of our mystery substance. On the reactant side, we have 16. On the product side, what plus minus 1 gives us 16? And the answer to that is 17. 17 plus minus 1, or 17 minus 1 is 16. A lot of times for this example, I would see students write 15. It's not correct here. 15 minus 1 is 14. So here for our mystery substance, we want an atomic number of 17. Mass number, 35 on the reactant side. What plus 0 gives us 35? 35. So what substance has an atomic number of 17? That would be good old chlorine. Has an atomic number of 17. Right. Let's do C. Or actually, let me see if I can find something a little bit different. No, we could do C. So for C, I have question mark goes to 9039Y plus 0 minus 1E. Okay. So mass number on the product side, 39 minus 1, 38. And since we only have one substance on the reactant side, it has to have an atomic number of 38. 90 plus 0 gives us 90. So what element in the periodic table has an atomic number of 38? That would be strontium, okay? Sr. And that's the identity of our mystery substance here. Let's take a look at a couple from 522. All right. So here we have question mark. This is letter A. Question mark plus 4018 argon gives us 4319K plus 11H. Okay. So let's figure out what the identity of our mystery substance is. So atomic number, product side, 19 plus 1 is 20. On the reactant side, 18 plus what gives us 20? 2. So our mystery substance here has an atomic number of 2. Mass number, 43 plus 1, I'll start with the product side. 43 plus 1 is 44. What plus 40 gives us 44? 4. So when I see atomic number 2, mass number 4, what do I think of right away? I think of an alpha particle. So 4,2 alpha or 4,2 He. Right away, I think of an alpha particle. Let me see. Let's do.
Can you do that one again?
Yeah, absolutely. Sure.
So how did we get?
So the general idea is that the atomic numbers have to add up to be the same on both sides.
Okay.
The mass numbers have to be add up the same on both sides. So let's start with the atomic number first.
Okay.
2 substances, 19
Yeah.
plus 1, 20. So what plus 18 would give us 22?
Okay.
All right.
Okay.
So that would take care of the atomic number. Mass
Gotcha.
number. 43 plus 1 is 44. What plus 40 gives us 44? 4.
Okay.
And then recognizing essentially mass number 4, atomic number of 2, that's got to be an alpha particle.
Okay. Yeah, I was still trying to do the subtracting like the other side, like the other ones, A, B, and C.
Yep. Yeah. So when you have these types of ones, when you have multiples on both sides,
Okay.
then it's sort of additive. It's really additive.
Okay. Okay.
Keep that in mind. And the biggest other thing is to watch out for these -1s with the electrons.
Yeah.
That sometimes gives students a little bit of an issue as well.
Yeah.
All right. Finish up by doing one more. Try to find a decent, somewhat of a. All right, let's do letter C. So we've got 10n plus question mark going to, and I wrote that too high.
Is this still 5.22?
Yes, it is. Yeah, this is just letter C from this point. All right, so we've got 10n plus question mark going to 14.6c plus 11h. All right, so product side, again, we'll start. 6 plus 1 is 7 for the atomic number. 0 plus what gives us 7? 7. So our mystery substance would have an atomic number of 7. Let's deal with the mass numbers. 14 plus 1 is 15. What plus 1 plus what gives us 15? That would be 14. And then we go to the periodic table. The only element with an atomic number of 7 is nitrogen. So that would be the identity of our mystery substance here.
Yeah, those are way simpler than what I was trying to do.
Yeah, they're not too bad. If you
No.
understand the idea that the atomic numbers have to add up to be the same, the mass numbers have to add up to be the same, it's not too bad. As I said, the one that gives students the most trouble is the beta particle with that -1, because a lot of times you go with a lower value, but in that case, because you're subtracting, you actually have to go with a higher value, to subtract, to make them sort of add up to be the same.
Okay.
Look, I'll show you one more. If you have 2813Al going to question mark plus 0 minus 1e, what would be the identity of the mystery substance? For the atomic number, the question is, what plus -1 gives us 13? And the answer to that would be 14. 14 minus 1 gives us 13.
1 negative.
Okay. Or 14 plus -1 gives us 13. The common mistake, again, I would see students make here is they would write 12. It's not 12 because 12 minus 1 is 11, or 12 plus -1 is 11. It's 14 minus 1. That's 13.
That's 13.
And then you'd have a mass number of 28, and that would give us an identity of silicon. You know, just for argument's sake, if you had, let's say, positron emission instead, where you had 0 plus 1e, then in this case, the atomic number of the mystery substance would be 12, because 12 plus 1 is 13. So then you have, and this doesn't exist, but you'd have 2812 magnesium. So that would be the difference.
Okay.
All right. Any other questions?
I'll keep working on it.
All right. Stay with it. Just go over some of the things we talked about tonight. Questions, that you had and such like that. And hopefully the quiz will be okay. I think it'll be. Nice to see you, Kim. Stay well.
Yeah, thank you.
All right. Take care.
Bye.